Now let's go ahead and continue our discussion on polar and nonpolar molecules, because we started that idea. We've talked about polar and nonpolar bonds, where one element has a greater electronegativity than another element in the bond between the two of them, and because of that, it creates a imbalance of charges towards the one with the greater electronegativity, and makes that element with the greater electronegativity partially negative, and by doing that makes the other element partially positive. Now that's within the bond. I don't want you to confuse polar and nonpolar bonds with polar and nonpolar molecules. Okay? There's a difference. Before you can determine whether or not a molecule is polar or nonpolar, you need to first of all figure out the bonds that are in it and whether or not they are polar or nonpolar, and how they're oriented. In other words, how they fit into the molecular geometry. Now, I'm going to go through and use examples in the book. So if you'll follow with me, in third edition, I am moving forward to page 192, nonpolar covalent and polar covalent molecules. I have some slides for this, but we can do it as well on the board relatively quickly. We have about, Mr. Parker, what do we have, about 20 minutes left in this? Thank you, sir. So they take a look here at the Ccl4 molecule, the Ccl4. Now we could go through and do the Lewis, and we could then figure out the Vesper and do all that, but recognize it's based on a tetrahedral. How do I know? It's got a central carbon with 4 chlorines around it. There are 4 bonds, so it's a tetrahedron. So I'm going to jump right to this depiction here. And at this point, I know you wouldn't be this rapid, but you could get to this point and you understand what I've drawn. Okay? So everybody understands what I've drawn right here. It's a tetrahedral molecule, carbon Ccl4. Now let's go ahead and indicate the polarity of the bonds. We have carbons and we've got chlorines. Which has a higher electronegativity? Chlorine has a higher electronegativity. So if I indicate those on the board, I'm actually going to change color here, because one of the things I don't want you to get confused with is that the indicators for the polarity is not another bond. Sometimes people get confused on that. So we know that the chlorines are going to be more electronegative, so the electrons are tend to be in that direction, right? The electrons are going to tend to be in that direction. They're going to tend to be in that direction. Are we comfortable with that? Because they tend to be at the chlorines, that tends to make this side positive. And so all I've done here is shown the direction of the polarity of the covalent bonds in the molecule. So if I were to look at just a single carbon-chlorine bond, I would say that in terms of that bond, the chlorine here is a partial negative. Actually, I'll put this in black so we can see it. And oh no, my marker is mixed in with the common markers. What am I going to do? I'm going to take the best one. That's what I want to do. Okay, so these chlorines become partial negatives. We've already indicated that by the sign. I just want to get you used to seeing this symbol again. And that makes the center here partially positive. Okay? So now, are you good with this? The bonds indicated on the 3-dimensional Vesper diagram for the molecule. Now here's the next point. I recognize that each bond has a polarity, but does the molecule as a whole have a polarity? Is one side positive and one side negative? No. Good. Because what we're showing here, remember, the tetrahedral, it's distributing its bond angles symmetrically. So each one of these bond angles is symmetric with every other bond angle. And every one of them is partial negative. As a matter of fact, it's partial negative to the same strength, because we're talking about a carbon-chlorine bond in every occurrence. In every situation, it's the same difference between the partial positive and partial negative. And so the partial negatives are all equal, and they're also equally distributed across the entire molecule. Which means when I come and approach this molecule, as a whole it's neutral. But as I look for positive and negative sides to the field, I can't find a discrepancy. It's perfectly symmetrical in all directions. Because it's perfectly symmetrical in all directions, let's say that I were to bring, some other field into it. I try to get this to bend one way or the other. If I brought a negative charge over here, or if I try to influence this molecule, I can't find one part of the molecule which is going to favor positive versus negative more than any other part. So I've got partial negatives and partial positives that are perfectly distributed across the entire molecule. And so this molecule, you can't have a positive side and a negative side. And so it is a nonpolar molecule. It's a nonpolar molecule because it doesn't have a positive side or a negative side. This nonpolar molecule is made up of 4 polar bonds. Each bond has a positive side and a negative side. But they're equally distributed throughout the entire molecule. Okay. Let's contrast that to the next one they use in the book is the AsCl3 molecule. Okay? Now from the very beginning, is AsCl3, is this a symmetric orientation? Is there symmetry in an AsCl3? What is the shape? Okay, it's a pyramidal. It's a pyramidal which is based upon a symmetric tetrahedral, but it lacks a bond and it replaces it with a unpaired electron pair, or excuse me, an unbonded electron pair. We had symmetry here, and we've changed it. So do we have symmetry here? No. This is not a symmetric, from the very beginning, this is not symmetrical. This is 3 legs and a couple of eyes stuck on top, right? It's a tripod with a camera. You look at the tripod back there, if the camera were down at the top of the TP section there, the leg section, I'd say, is this symmetrical? No, it's not symmetrical. One side has legs, the other side has a camera on it. It's different. So it's not symmetrical. You know from the very beginning, this is not going to be a nonpolar molecule. It's going to be a polar molecule. Why? It's going to have one side behaving one way and one side behaving differently. Okay? And as we look at this, chlorines and arsenics, how do they line up with electronegativity? Arsenic is a 5. Chlorine is upper right 7. So chlorines have a greater electronegativity there as well. So we're going to have a bond that goes out in this direction. It's polar to the outside. Okay. But we still have the issue of symmetry. It's got the same type of bonds, but it's not symmetrical. Now, because it's not symmetrical, there's not a perfect balance, then this molecule here is going to be a net polar. This is a polar molecule, example of a polar molecule, contrasted with this, which is a nonpolar molecule. Now, I'm going to go ahead and erase the one I just wrote and leave the Ccl4 up here, because in the book they go to the next example, which goes back to what we talked about earlier about perfectly nonpolar molecules are only formed between homonuclear diatomics, right? We said that before? Okay, but now let's go over to this molecule here. I'm going to erase this one. We're good with me erasing it? Okay. What if we were to change this arrangement up a little bit and have it be a Cl3 F. Okay. Okay. We know that the polarity of the bond between carbons and chlorines are going to favor the chlorine with higher electronegativity, so it's going to be in that direction. What about carbon and fluorine? Well, let's look over here. You got carbon and fluorine here. So where's the direction going to be? Towards fluorine. Okay. So in terms of, they're all polar bonds, and it's in the form of a tetrahedral. So they're all polar, and they're all tetrahedral, so it's symmetric. So in terms of its shape, it's symmetric. But now, stop for a moment and think, in terms of the degree of polarity, we're going to be comparing this bond, which is a carbon chlorine, and this bond here, which is a carbon fluoride, fluorine. Okay? Which one has a higher electronegativity, chlorine or fluorine? Okay, again, good. Looking over at the chart, chlorine is lower on the periodic table. Fluorine has a higher electronegativity than chlorine does. So when I compare this bond between carbon and fluorine with a carbon and chlorine, we know that they're both favoring the chlorine and the fluorine. They both have higher electronegativities than carbon, but are they the same bond, or the same charge differential? In other words, if fluorine and chlorine were exerting the same amount of force, they would be the same all the way around, and it would be symmetrical. But we know that fluorine exerts more force, more electronegativity. It wants the electron even more than chlorine does, okay? Which means that this, compared to these two, this partial negative up here for fluorine is going to be greater than the partial negatives for these chlorines. This is going to be greater. It's pulling on the electron harder than the chlorines are. Okay? And because it's pulling harder, it's getting it more often. It's making this partial negative greater than the partial negative of the chlorines. And because of that, if we were to go through the center of the atom, let's do it that way, we would have, in the big picture, one side of this atom which is more negative than the other side. Because fluorine is pulling the electrons this way harder than any one of these chlorines is pulling the electron in the other way, in the other directions. It's going to be slightly more partially negative at the fluorine side, which is also then going to say this molecule as a whole is slightly more negative on the fluorine side. So it's not symmetrical, which makes it polar. If this were another chlorine, it would all be symmetrical, but it's not. So since it's not a chlorine, does it pull more or less? It pulls more. Okay, it's more negative. It makes the whole thing polar. Yes, ma'am?
Does a partial charge in the middle not matter?
No, it's the pivot. It doesn't matter. It's like an octopus. It's in the center, but you've got to deal with the arms first on the outside. Yes, ma'am?
So if it's symmetrical, it's nonpolar, and if it's not polar?
If it's symmetrical, it has the possibility of being nonpolar. If it's symmetrical in its shape. But in order for it to be symmetrical in its charge, it first of all has to be symmetrical in its shape. So check the shape. Is the shape symmetrical? Yes or no? If the shape is symmetrical, then it may be nonpolar.
But it has to have all the same.
Right, then it would have to have all the same charges. All the same electronegativity differentials would have to be the same. So what practically speaking, what are you looking at? You're looking at a shape which is first of all symmetrical. So it could be a tetrahedral. It could be trigonal. And it could be linear, right? So it's either going to be, for it to be symmetrical, let's just think through this. I haven't thought through it this way, but let's for a moment reason together. And if I make a mistake, speak up. Here's my thinking now. In order for it to be nonpolar, it'd have to first of all be symmetrical, which would be a shape like this. a shape like this, or a shape like this. It's got to be one of those three shapes. Or a shape like this. We talk about two that are stuck together, right? Just two bonded. So it's got to be a linear, a trigonal, or tetrahedral. If it's not one of these shapes, again, with the scope of this course, we talked about octahedral and all those other, larger molecules, but we're not going there in this course. But for this course, if it's got to be one of those shapes to be polar, or excuse me, to be non-polar. If it's not in one of those shapes, it's polar. Okay? So if it's bent, if it's pyramidal, it's polar. If it's one of these, it might be nonpolar. But then what we've got to do is go between the central, in this case, these two have to be exactly the same element. If they're not the same element, it's polar. In every one of these, we just look at the outside elements. And if they are the same, it's nonpolar. If they're different, it's polar. So this would have to be an AB2, this would have to be an AB3, and this would have to be an AB4 molecule. And this would just be an A2, homonuclear diatomic. You see? Does that make sense? Is that right? Does it sound right to you? Okay, so symmetric shapes first, has to have a symmetric shape, and second, every one of the exterior elements has to be the same. If it's not symmetric and they're not the same, it's polar. If it is symmetric and they are the same, it's nonpolar. It's a good summary. I'll work that into the way I teach the course. Now, on the bottom of 193, they talk about the Ccl4 molecule. Ccl4, if we draw Ccl4 in the two-dimensional Lewis structure, and that they show this to you because it's easy to get this one messed up. We did this on the PowerPoint slide earlier for the Lewis structure. I'm not going to draw the other valence electrons, okay? Just remember they're out there. I'm not going to draw the 6 dots around each of the fluorines right now. The C2F4 molecule. Pardon? Okay. So C2F, this is the two-dimensional Lewis structure, right? Because if this were drawn in three-dimensional Vesper, it would look like this. C, C, because they're going to push apart here in a trigonal type of pattern for these as well, because they're going to be equally separated. You see the difference between this and this? Now, if you try to assess whether or not this is polar or nonpolar, and you do it with a two-dimensional Lewis structure, it's not going to work. Because you could look right here and say, wait a minute, if I draw a line through the center of the atom here, look what I've got. I've got this side over here, which is not the same as that side. It's not symmetric, fails, right? If you draw it, if you try to assess it on the two-dimensional. But if you draw the three-dimensional and you do it right, now you look at it and say, wait a minute, if I cut it down here, it is a mirror image. It is symmetrical. If I draw it through here, it is symmetrical, mirror image. As long as I divide it through the center of the molecule, and both sides are mirror images of each other, it's symmetric. So, as I go through here, hey, guess what? It's symmetric. See, so when I draw it in an appropriate three-dimensional, then I can assess whether or not it's symmetric or not. It's symmetric in its shape, and we have the same bonded elements on the outsides, meaning that the electronegativities are the same, the strength of those electronegative bonds are the same, meaning that, yes, this is now a nonpolar molecule. If we try to assess it here, though, you very easily could say it's polar because it's not symmetric in its shape. Even though it has 4 of the same element, you would get it wrong. Here you say, yes, it is symmetrical, and that would be correct. So it is nonpolar because it's symmetrical in both its shape and its construct with the same exterior elements. Bam. Tell you what we'll do. On Monday, go ahead and work the on your owns. It's on your own 510 that talks about classifying the molecules as polar covalent or nonpolar covalent. We'll go through the on your owns and then probably do the labs on Monday.